Here's a quick description of how to do the barometric pressure calculation. The absolute zero one is really just a straight line, so that's not that big of a deal. You just have to graph and solve an equation. So the barometric pressure one, though, the books, the equation is a little confusing. So I think it's important that you understand where it's coming from. And so I think that's a big risk in chemistry, is just to sort of follow the equation and not think about what actually is happening. And I think if you think about what's actually happening, where the numbers come from make a little bit more sense. Okay. All right. So we've got this gas at constant temperature. So if you think about the ideal gas law, PV equals nRT, it's going to be functional for both the first state, okay, and it's also going to be true for the second state. It's going to follow, right? Now, in this case, in number of moles is not going to change. Obviously, the gas constant is not going to change, and the temperature is not going to change. And so those are all going to be the same at both states. So then that allows us to simplify this then back to the sort of standard rule of P1, V1, P2, V2. So now the volume differences are easy to calculate. The pressure difference, a little bit harder. Okay, so let's think about the volume differences first. So we know when we measured the water in the flask and then we just used the conversion, the 1 gram of water is equal to 1 mil, we can say we've got in this case, the case I've just drawn, we have 0.54 liters. Okay, so that's V1. Now V2 is going to look a little different because if you remember right in V2, okay, we've dumped a lot of water on this side, right? And so this side is going to raise up, but not all the way. As long as we didn't have the seal, as long as we had a good seal, it's not going to rise up all the way to being even, but there will be a difference there, okay? So the volume's getting smaller, and it's getting smaller by whatever this amount is, delta V, okay? So we can calculate that delta V by just taking the cross-section of the tube times how much the closed side raised, okay? So in this case, the case I have here, this is like 18.3 or something like that, 18.3 centimeters. So this rose 18.3 centimeters. Okay, so the volume shrunk 18.43 centimeters in the tube, but then we got multiply times cross section to get volume. So the delta V here equals the difference, 22.5 minus 4.2 times 0.26. Okay, so this is in centimeters, that's in centimeters, that's centimeters cubed. Centimeters cubed is the same thing as milliliters, so that ends up being 4.8 mils, okay? So now V1 equals 0.540, and V2 equals V1 minus this difference, so 35 point, oops, sorry, it's in decimals, 5352. Okay? So those are our volumes. Okay, so now we've got a volume on each side. We've got P1 times 0.54 equals V2 times, or P2, sorry, 0.5352 times P2. Okay? So now we have to figure out how to relate the pressures to each other. Okay, so if we know the pressure in the flask at any time is equal to the atmospheric pressure plus whatever extra water is above this in terms of the mass. Okay, so P1 equals P, the barometric pressure, plus whatever this difference is here. Okay, so in the first case, the difference is 1.8. Okay, and it's going to be 1.8 plus 1.8 centimeters of water. Okay, in this case, P2 is going to equal P bar plus, in this case, the difference here, which is 10.8. Okay. Now what we have to do okay, we know excuse me. Okay, so what we can do if we want is we can say, well, then the, if P bar in this case is identical, okay, we could potentially relate P1 to P2, or you could just go ahead and substitute in for both of these if you wanted to, okay, or the way they do it in the book is then they say, okay, if I want to make P2 expressed in terms of P1, okay, we know that P bar is the same, then it makes sense that P2, or P1, let's do P1, no, let's do P2. P2 equals, okay, P1 minus 1.8 plus 10.8, okay, centimeters. So all I've done there, I solve for P bar, then substitute that in to there. So you could say that P2 then is equal to P1 plus 9.0. Okay, so then you could substitute that into here, okay, and you'll get P1 times equals 0.5352. We'll substitute this in for P2, P1 plus 9.0 divided by 0.54. And then you just have to solve for P1. And in this case, if we solve that for P1, you'll get something on the order of P1 equal to P1 will be equal to 1,003 centimeters of water. So now we have to substitute this back in to there, okay, which means that P bar would then be whatever this is minus 1.8. So basically, if you consider significant figures, 1,001 centimeters of H2O, which then you convert with 13.7, you get P bar in this case equals 745 millimeters of mercury. Okay, so my guess is the answers are going to be a little bit worse than that, but if you break it down like this, if not just try to memorize the equation, I think it makes a lot more sense. So if you still have questions, please come and see me.